Hi everyone, welcome to Chapter 7. It's titled Gravimetric and Combustion Analysis. Let's get started. So the first thing to figure out is what is gravimetric analysis? This type of analysis uses the mass of a product to help calculate how much you actually started with in the beginning of the reaction. Back in the 1900s, T.W. Richards actually got the Nobel Prize because he measured the atomic mass of silver, chlorine, and nitrogen using gravimetric analysis. These procedures were the hot topic back in the 18th and 19th century. Actually, and even it says even before it was long understood. So they knew that what they were getting was correct because they tested it against other methods, but they really didn't know how it was working at the time, which is kind of interesting. Nowadays, gravimetric analysis isn't used as much. It's largely been replaced by instrumental methods. Obviously, they're faster and they're, less work. It's less tedious. But if you're really skilled in the lab and you do gravimetric analysis, that is probably one of the most accurate methods available to produce standards for instrumental analysis if you're really good at it. So there's definitely people that still do this type of analysis. A really simple example that shows gravimetric analysis is the determination of the chloride ion by the precipitation of the silver ion. So here I'm just showing you a net ionic equation, which shows you that 1 mole of silver ion plus 1 mole of chloride ion precipitates out a silver chloride solid compound. So you could backtrack or back calculate what the molarity of the chlorine originally was in the original sample. So the mass of the AgCl tells you how many moles of AgCl were actually produced. And if you notice, it's a 1-to-1 ratio to everything there. So if 1 mole of AgCl was produced, it came basically from 1 mole of silver ion or 1 mole of chlorine ion. So a simple example is written down here. So it says 25 ml solution containing sodium chloride plus potassium chloride was treated with excess silver nitrate to precipitate 0.4368 grams of silver chloride, which has that molecular weight. What is the molarity of the chloride ion in the unknown? So you know that you received a 0.4368 grams. That's your product, right? That's what you got. So you go ahead and take that 0.4368 grams of AgCl and you convert that to moles of AgCl. So you use 143.321 on the bottom, 1 mole of AgCl on the top, and then you just use your simple mole to mole ratio. In 1 mole of AgCl, there's 1 mole of chloride ion. Now, it doesn't matter that you have two basically reagents that have a Cl, right? Because it says there's NaCl and KCl, but it doesn't matter because they're all in the same solution, and both of them are 1-to-1 mole ratio, so it does not matter. So you would just figure out what the moles of chloride ion are and then divide that by the amount of the solution, which is 25 mils or 0.025 liters. If you do all that, you get 0.01219 molar. So that's the concentration of the chloride ion that started in the unknown solution. The reason you got that was because you measured how much product was received at the end of the reaction and you backtracked it with stoichiometry back to the original solution. So this is sort of very similar to what we used to do in general chemistry, just it's going to get a little bit more complicated as we get further and further. So you probably already noticed that if we're going to do a gravimetric analysis, you're going to need something to precipitate out of your solution. The whole point is that you weigh something at the end of the reaction and then backtrack the calculations back to the original solution. So we have to get precipitation to happen. Ideally, you want your precipitate to be insoluble in the solution that it's going to end up in. It needs to be easily filtered. It needs to have a known composition, known and constant composition, and the precipitate should be stable when you heat it. So if you want to remove any traces of solvent or anything, you don't want it to decompose when you're trying to heat it. So it should be pretty stable when you're heating it. And really, there isn't a lot of substances that really meet those requirements, just how they are, but there's things that you can do to actually optimize their properties. So we can optimize the properties, but a couple things I want to talk about before optimization, which basically includes crystal growth and nucleation. You got to remember that the main thing is that these things have to be easily filtered. Because think about it, if they're too small, it's gonna go straight through the filter, and you're not gonna have anything at the end to weigh. If they're too large, it's gonna clog whatever filter you have that you're trying to use. Now, there's a name that they put to things that are too small to be filtered. Those are called colloids. And I put there what with a question mark because it is a funny name. But colloids are particles that are between 1 to 500 nanometers in diameter. There is a picture in your book, it's figure 7.1, that shows the particle size distribution of colloids formed when iron sulfate is oxidized. And you can tell they're super tiny little particles, but they're even smaller than the regular particles that would be filtered in a normal precipitate. So what defines them is the fact that they're between 1 to 500 nanometers in diameter. So they are larger than molecules, but they're too small to actually precipitate and filter. So they remain in the solution. So you don't want that, because that's not going to help you with weighing, like I said, weighing your product. There's also another table in your book, it's table 7.1, which shows representative analytical precipitation. So basically, it tells you what species is being analyzed, what's the precipitated form that you would weigh, right, that you would weigh out, and then some of the interfering species. So for example, the example that we did, it analyzed the chloride ion, and what precipitated out was silver chloride. So that's what we actually, and what we weighed was also silver chloride. And if in that particular reaction you have some interfering species, like bromide would interfere with it, iodide would interfere with it, sulfide. So it tells you, it's a really handy little table that if you were trying to create a precipitating reaction, you would probably go to this table and see, okay, which one of these would be most helpful for me to use. One of the things that you can do to optimize your precipitate would be to actually grow your crystals. So how do we do that? Well, crystallization occurs in two different phases, okay? There's the first phase, which is called nucleation, and the other one, which is called particle growth. Now, in nucleation, the dissolved molecules or ions that you're using, they form small little tiny aggregates that are capable of growing into larger particles. And your book tells you the nucleation actually tends to occur on pre-existing surfaces that attract and hold solutes. Think of scratch on a glass surface, okay? So there's a potential for crystals to start growing in that little divot of the glass that will actually initiate nucleation, which is an aggregation of molecules to form larger molecules. Just think of what water does. If you have a piece of glass and the glass has like a scratch on it, if you pour water on it, there's water molecules tend to stay within the little divots of that scratch. It's kind of like that. The molecules tend to aggregate in certain pre-existing surfaces that attract and hold solutes together. Now, what's particle growth? In particle growth, the solute molecules or ions add to an existing aggregate to form an actual crystal. So both of these parts are really important. You want these things to form small aggregates, but then once they have the small aggregates formed, you want it to actually get bigger and bigger, depending on to what size you want the crystal to be. But the first part would be the nucleation. The second part would be the actual particle growth. So the adding to whatever existing aggregate you have to actually form a crystal. So remember, all these things that we're doing are to make our crystals. This is all in solution. We're trying to make our solid crystals, but it's all starting from a solution. So what happens when the solution that you are using has more dissolved solute than should be present in equilibrium? What happens is you get supersaturation. And this is a bit of a problem, because if you have a solution that's supersaturated, the nucleation process actually happens a lot faster than the particle growth. So basically, many nuclei actually form before there's time for the crystal to actually grow and get larger into bigger particles that you can actually filter out. So if it's highly supersaturated, the particles that you're going to get are actually going to be really tiny. Because again, in a highly supersaturated solution, nucleation proceeds a lot faster than particle growth. So there's no time for the particle to actually grow into a good sized crystal. So you're going to have really tiny particles in this supersaturated solution. In a less concentrated solution, the nucleation is a lot slower. So the nuclei actually has a chance to grow into larger, more, filterable particles or tractable particles like your book says. So what are some techniques that actually promote particle growth? Obviously, you can raise the temperature. If it's too concentrated in there, just raise the temperature. If you do that, you increase your solubility. If you do that, obviously you're going to decrease your supersaturation. Another thing you can do is keep the volume of the solution really large. Obviously, if you put more volume in there, it's going to be more dilute, so it's not going to be as concentrated. Another really easy thing to do is actually just add the precipitate slowly. Don't mix it really, really fast. Give it some time to equilibrate and then add a little bit more. As an example, your book tells you that the solubility product for, let's say, a barium sulfate is 1.1 times 10 to the negative 10, okay? A saturated solution of barium sulfate contains 1.05 times 10 to the negative 5 molar of each of those ions, right? The barium ion and the sulfate ion. Now, a supersaturated solution would contain 2.1 times 10 to the negative 5 molar of both ions, barium ion and the sulfate ion. So that supersaturated solution has twice as much of each ion as should be present at equilibrium. And like I said, you don't really want that because you're not going to give the particle enough time to grow into an actual good-sized crystal. So far, we've only talked about precipitation when it's carried out by mixing a solution of precipitant with a solution of analyte, kind of like the problem that we did previously. There's another type of that you can have a precipitation. It's called homogeneous precipitation. That's when the precipitate is actually generated really slowly, but from within an initially homogeneous solution by chemical reaction. The good thing about this thing is that, first of all, we're not mixing two things together, right? It's actually, the precipitation is actually happening from within the solution. And when this happens, it's usually really slow. So when the precipitation is slow, what is dominating? Nucleation or particle growth? It's going to be particle growth. And that'll give you larger, purer particles that are really easy to filter versus nucleation, which gives you tiny particles that are not easy to filter. All right, guys, that's all for this short video. It's a lot of terms that we've talked about, but basically all it is we're talking about gravimetric analysis. For that to happen, we have to weigh something out. So we went into the discussion of how do we make these precipitates, and we talked about how do we optimize the properties of these precipitates, and soon we will do problems with this. But the second part of the video is going to talk about a little bit more about terminology that we need to understand before we actually do problems. All right, guys, see you later.